Let's get started. I can't see my icon. And why is OBS so off center? So first, quickly, let's normal size this. We did hit 60%. We're at 64 right now. Actually, let me refresh and get you the latest up-to-date number, unless you're watching this on YouTube or the VOD elsewhere. 64%. We're at 64% right now, so you will be able to make up one application objective from the previous homeworks. So the submissions are already open for genetic algorithm, but I also reopened up the submissions for homework 1 and homework 2 for the first two assignments. So you can still submit. The feedback will say that you can't get credit on the application objectives, but I will look into the feedback. I'll make sure you get points if you complete one of those. If you have, like, for example, for point of sale, if you have 1 or 2 AOs already and you want to get one more of there on that assignment, it will show you a grade of 0 AOs no matter what you get, the way the grader is set up right now. But I have a script that's going to parse the feedback and see if you earned credit for that application objective, and you're going to get your points. You're going to get the points for the ones that you had previously, and you'll get the points that you earned. Like, whatever's the most fair thing to do, that's what I'm going to end up doing. So if you ever had a submission with an application objective complete, you're going to get credit for that application objective, unless you go beyond your 1. So you can only make up 1 application objective after the checkpoint date. But if we hit 80%, which we're pretty far away, and this number has really lost its momentum. So don't don't count on this. If you're like, well, I'm just going to do 2 AOs just in case, just be aware that a good portion of the class, for whatever reason, just historically speaking, won't fill out the course evals. It's pretty hard to get up to 80%. I hope you do make it. I do want to give you 2 opportunities here. But if we don't hit 80%, even if it's 79%, it is what it is. So we need quite a few more students. If you're really looking at that 80% and you want to get those past 2 AOs, maybe that's what you're going to try to do to not have to take the final, or maybe that's what you need to get in range where the final can get you up to an A. Whatever your situation, spread the word, help out, and get people to fill this out. But we lost a lot of momentum. We barely crawled across the 60% mark, and we only made it 4% past that. So it's it's definitely a logarithmic rate, logarithmic increase in response rate. Unfortunately, I don't know why it's so hard to get students to do this. Like, if I don't bribe you with something like this number usually floats around 30% in any course I've ever had. If I don't promote and bribe, 30% is this is the only response rate I'll get. I don't know why students are so adverse. It doesn't take that long to fill out the course evals, but it is what it is. I don't know. The feedback is valuable. I'm willing to bribe you for it. But at some point, I mean, there's only so much I'm going to do to try to get everybody to fill it out. All right, so today what we want to do, so we've actually covered all of the content I need to cover in this course. There's no new content coming up. But what I want to do today, just like the last, pretty much every Friday in the course, or at least the last Friday of each learning objective, and the last 3 Fridays in the course in general, just go over review and examples to try to make it more clear what we covered. Why do I always have trouble doing this? Make it more clear what we covered over the past week in this case. So let's look at graphs and see some examples of graphs, and hopefully have graphs make more sense after 50 minutes of talking about it some more. Bad bot repetition. So let's talk about it. So I want to go through this graph example. This is the graph that we talked about in the slides. It's the same graph with the early days of the pre-internet, the alpha release of the internet, effectively. And I want to run the debugger. Let's back this up a little bit. Let's go right to the beginning. Why not? run this in the debugger and watch what actually happens through this graph. Because this graph class, you use this in the current homework assignment, of course. And then breadth first search, I want to go through a run of breadth first search and make sure that you understand how this code relates to what we did in the lecture slides the past few lectures. So let's run this thing in the debugger and take a look at everything. Yeah, my video's stuttering at times. Yeah, unfortunately, that I can see my bit rate. I don't think I can. Maybe I can lower it during stream. The quality will go down here. You know what? I don't even want to mess with it. I'm just gonna leave it, just in case it breaks even more. Yeah, someone's downloading all the internet. But I have plenty of internet. I mean, my daughter's watching YouTube right now, but there's no possible way that would take up all our internet. I mean, well, let's take one quick side trip. There's no way it's it might be Twitch not ingesting the data fast enough. There's no way my internet's slow. Goodness, all the ads on this. Wish I could just skip to the upload. I'm only concerned with my upload time right now. My upload. Jesse Doxson his IP. Yeah, you can have my. I never understood that. Why people want to protect their IP. What's somebody gonna do with my IP? Yeah, so it looks like this is Twitch's a problem on Twitch's side. I'm only uploading at 6. I have it set to 6K. 6 megabits per second upload, and I have 17 available. It's not my internet. I guess I can't, as much as I like to, I can't blame Verizon right now. It might be Twitch just not able to ingest fast enough. Or possibly my PC. Would that be possible? I have quite a bit of power in this thing. So let's run through this in the debugger. First thing we do is create a new graph. The graph is, let me get this positioned a little better. This graph is going to initialize its 2 data structures, one for nodes and one for all the edges. The edges are represented in an adjacency list, which is going to store all of the neighbors of each node. And then we're going to add nodes. We're going to add each node with an index and the actual value for that node. So this node is going to be a node for UCLA, and I'm arbitrarily giving that the index 0. With these indices, the most important part is that no 2 nodes have the same index. These have to be unique. So when I add a node to this graph, I'm going to add it to my nodes, my nodes map. That's going to map index to the actual value stored at that node. And then I'm going to initialize the adjacency list for that node. I'm going to initialize the adjacency list to an empty list. So I'm going to say this node has just been added. So there's no way that it has any neighbors yet because we haven't added those. We haven't added those neighbors yet. We haven't added any edges. Do lecture in Discord when Twitch isn't working? No thanks. If anything, I would probably switch to Zoom as a backup. Actually, I would just cancel lecture. let's be clear there. At this point, I would cancel lecture because we're at the home stretch. We're winding down. Earlier in the semester, I'd probably back up on Zoom. I'd probably make a Piazza post and hope it goes well. Hope people see it. So for each node, we're going to add it with a particular index, a particular ID, and then the value. Here, this is a graph of strings, and the nodes are just represented as strings. YouTube Live, but I don't have it set up, is the problem with that. If I had it set up, I would, that would be my backup. That would be the one that would make the most sense. So we're going to add these nodes for each node, doing the same thing, adding it to the nodes map, and then adding a new list to the adjacency list for that particular node. Oops. So let's step over those. And then once we have all the nodes added, we can take a look at how our graph is shaping up so far. We can see all of our nodes, These are all map entries mapping the index to the actual node value. And we can see they're out of order as we expect from a map. Map order doesn't matter. Order is irrelevant. We're going to get, to us, some random order. There is organization to this chaos, but for our purposes, this is just some random order. And then we have our adjacency list. We're mapping each value, each node ID to an empty list because we haven't added any edges yet. Now we're going to start adding those edges, and we add edges by ID. Everything that we do with a graph, we're going to work with those integer IDs. We're not going to work with the actual values of any of the nodes at any point. We're only going to look those up. We're only going to look up the value at a node when we actually want that value, when we want to get away from the graph and get like an answer out of the graph. That's the only time we're going to look up a node. Everything about our graph is designed to work with integers, with those integer IDs. So we're going to get those. So we have all of our nodes set up, and we're ready to start adding edges. We're going to add edges by ID. So this add edge 0, 1, we're saying we're going to add an edge 0, 1. We're going to add an edge between UCLA and Stanford. So our UCLA 0, UCLA 1, Stanford, we're going to add those edges in this graph. When we do that, we're going to add the edge to each of those nodes' adjacency lists. Oops. And then we can look at our adjacency list. The adjacency list for node 0 has the node 1 because 0 and 1 are connected by an edge. And the adjacency list for node 1 has the node 0 because 1 and 0 are connected by an edge. Then we keep adding edges. 0 and 2 are also connected by an edge. So we're going to add that to both lists. So now 0 is connected to nodes 2 and 1. Node 1 is connected to 0, and node 2 is connected to 0. So each edge is represented in this adjacency list twice, once for each end of the edge, each node in that edge. And we continue to do this, add it to our adjacency list. 0 is connected to 1, 2, 3, and 4. 0, if we look up the adjacency list, we say, hey, 0, what are your neighbors? It has a list containing those nodes 4, 3, 2, and 1. Node 3 is connected to 0 and 2. Did this already run? It must have already ran. Where was I looking? No. Oh, I was looking at 1. Oh, because it's index 3 in the map. Those indices. Never mind. I don't want to go down that road. But node 1 is connected to 0 and 2 at this point. So we have a list 2 and 0. So it's a list of all the neighbors of each node. I think we get the idea there. And stop me at any time with questions if you have them, by the way. So once we add all of the edges to this map, that populates our adjacency list. And we can see our adjacency list for each node is going to contain all the nodes that are connected to it by an edge. So like node 10, which does happen to be, actually let me just look in the debugger, which happens to be Carnegie. Node 10 is connected to nodes 11 and 12, which happen to be Harvard and Case. This is representing the same graph and the same data that we had in the slides, but we're doing it programmatically. We're doing it using this graph data structure now, and using specifically an adjacency list to store all of the edges between any two nodes. So this information here, this is our graph. We have one graph at 8:15. It's on the heap. Here's an adjacency list and nodes, both on the heap. And that's how we have all the information of our graph. All the nodes and all the edges. really bugging me. Never seen OBS saying this before. All right, so we have our graph. Let's run breadth first search starting at node 0. So we're going to jump into the breadth first search code. This code is going to run the same thing that we saw in the lecture slides. But let's step through this one step at a time to make sure everybody understands how this code relates to what we saw in lecture the past few days. So we're going to use a few data structures to keep track of the information as we go through this algorithm. We're going to use a set to mark the nodes that we've explored, and we're going to use a queue to track which nodes we're about to explore. We're going to initialize both these data structures with the starting node. We're going to say the starting node has been explored, and we're going to enqueue the starting node to say this is the first node that we're going to explore the neighbors of. And we're using the queue class that we built in lecture before. So we have our explored is just the node 0, and to explore, we're looking at the node 0 in the queue. The queue just has one element. And we're going to run this algorithm as long as there's still something in the queue. As long as there's something in the queue, we're going to keep iterating and keep processing the next node in the queue. So the first thing we're going to do is go to the queue, dequeue the first element, and get the node that we're about to explore. Which I realize I use the word explore to mean two different things in this, if that's confusing. So when we have a node to explore here, that means we're about to explore the neighbors of that node. And when we explore one of their neighbors, we're going to mark them as explored. But they can be explored and also in the queue to be explored to check the neighbors of that node. I really should rename these variables to make that more clear. But the node that we're currently exploring the neighbors of, we're going to look at the adjacency list and get all of the neighbors of that node. So we're going to iterate over the neighbors of this node. We're going to look at the graph, get the adjacency list for node 0. So we're going to iterate over the nodes 4, 3, 2, and 1. We're going to check the first thing we do for each one of those nodes, which our node, we started at 4. The first thing we're going to do is check if we've already explored this node. If we already explored it, that means it's either in the queue or it's already was in the queue and got dequeued and we already explored all the neighbors of that node. In either case, we don't want to process this node again. So 4, we did not explore yet. We've only explored node 0 at this point. So we're going to process this node. I'm going to just print to the screen that we're exploring this node. Enqueue it into the queue and mark it as explored. So now our explored set has the nodes 0 and 4, and our queue, we enqueued the node 4. We're going to keep doing this with, oops, I didn't want to jump ahead that much. Is there an easy way to see that? So after we explore all the neighbors of node 0, which were 1, 2, 3, and 4, we have all of those nodes marked as explored. They're in the explored set. And the to explore queue is going to have the nodes 4, 3, 2, and 1, all of the neighbors of 0. Now the queue is not empty, so we're continuing. We're going to dequeue the first node in the queue, which is 4. And we're going to iterate over its nodes. So we dequeued 4. It's no longer in the queue. And we're going to look at our graph and get all the neighbors of 4. So all of the neighbors of 4 are 8, 6, 3, and 0. So we're going to check node 8. We would expect this to be node equal to 8. And we're going to check if it's explored. Explored, which is apparently a pain. Oh, can I see him just here? So we've explored nodes 0, 1, 2, 3, and 4. So node 8 has not been explored yet. So we're going to explore it, add it to the queue. Let me just get out of there. Add it to the queue and add it to the explored set. So now 8 has been explored, and 8 is at the back of the queue. Next node, we're going to look at 6. 6 has not been explored yet, so we're going to enter into this conditional. I'm going to remember to jump over my queue because I don't want to look at the queue code again. And explore 6, add it to the queue. So it's marked as we're going to start exploring the neighbors of 6 when it gets to the front of the queue. Next, we're going to check the node 6. There we go. The node 3. Now, this is our first case where the node has already been explored. Since the node is already in the explored set, we're going to skip over this and not do anything. Node 0, that's already been explored, so we're going to skip over it. We never want to visit a node more than once. It's already been explored. We're not exploring it again. And that's how we avoid an infinite loop here, or else our queue would never be empty. We would just always be adding the same nodes over and over and over again. So now our queue is not empty. So we dequeue the next node, which is 3. We're going to dequeue 3. So node to explore is going to be 3. And we want to look at the neighbors of 3, which is 4, 2, and 0. Now we already know that all of those nodes have already been explored. So we're actually not going to get anything done on this one. Where's my... All those nodes are already in the explored set. So we're actually not going to get anything done when we explore 3. So if nothing happens. Next node, we're going to explore node 2. Node 2 has neighbors 5, 3, 1, and 0. I don't think we've explored 5 yet, right? I think that's the one I want to talk about. It's where I'm going to talk about something different. So node 5. So when we explore node 5, we're exploring node 5. We're going to mark it as explored. We're going to add it to the queue. At this point, so for your homework for LT5, LT6, and A01, you're going to want to modify this breadth first search code. Take this, put it in your code, and modify it to get the information that you need. So say you're finding the distances in LT5. Right here, you have access to all of the information that you need. You have the node that you're currently exploring, the node... I gotta collapse some of this. Where the hell is node to explore? That variable just go away? Oh, because I'm inside the loop? Oh, that's annoying. But I have access to the node to explore, which is 2. So I know right now what I'm doing is exploring the neighbors of node 2. And I know that I'm currently finding the neighbor of 2, which is 5. So I have access to the node where I'm coming from and the node that I'm going to. So this is where you would want to update a data structure, preferably a map, which is going to store the distances from the start node to any node in the graph. So if you have the distance from the start node to the node that you're currently exploring the neighbors of, which is 2 in this case, if you have the distance from the start node to 2, you can update your data structure to get from the start node to 5 by taking the distance from the start node to 2 and adding 1 to it. You add 1 to it because you traversed 1 extra edge to get from 2 to 5, and that's the distance to 5. So how do we know the distance from the start node to 2? Well, when we explored 2, we did the same thing. When we explored the node that discovered 2, we did the same thing. You just always do that same thing. And how that starts is when you explore the very first nodes, you know that the distance from the start node to itself is 0. So when you explore those first nodes, you're adding 0 plus 1 to get 1. And then the next nodes, you explore their neighbors. You take 1 plus 2, you get 2. You explore their neighbors. 2 plus 1, you get 3. And you end up, just from initializing some data structure saying the distance from the start node to itself is 0, then every time you discover a new node inside this conditional, you say, well, what's the distance from the start node to the node that discovered you? Add 1 to that, and that's your distance. So hopefully that clears up a lot of LT5 questions. And then these other nodes we've already explored. We've already explored 1. We've already explored 0. So back to the queue. What's the next node to explore? It's 1. Let's explore its neighbors. 2, we've explored. 0, we've explored. And we're on to the next node. Next node is 8. 8, we should find some new stuff if we look at our graph. 8, 11, 7, and 4. I don't think we've explored all those, but let's let the code tell us. Let's let the debugger tell us. 11, we have not explored, so we're going to explore it. Add it to the explored set and to the queue. Yeah, chat is quiet as hell. It has me nervous, especially with the bitrate fluctuating. I think it's fixed now. I decreased the bitrate. So it's not trying to overflow things. But yeah, it had me nervous with chat being so quiet. I think most people finished all the required LTs for this LO. I don't think so. I don't think that's the case. Once I get through this example, I can look up the numbers, but I don't think so. Node 11, we explored. We just added to the queue and the explored set. 7, we didn't explore. Add it to the explored set in the queue. Node 4, we have explored, so we're going to skip that one and go to the next one. You get the idea? Anybody got questions on this? I think you get the idea by now. You explained a little bit more about how breadth first search finds the shortest path. I thought they simply showed us all of the possible paths. The way that the algorithm works, the fact that it is breadth first search, it will always find the shortest paths. And that's a feature of the algorithm. And the quick proof of that is assume breadth first search did not find the shortest path from one node to another node, then that means the algorithm violated its own. The algorithm violated itself. It didn't do what it's supposed to do, because it would have found that shorter path by finding that node sooner than it actually did. There's no way for the algorithm to take longer if it's always starting at the start node and then expanding by one node and expanding by one node and expanding by one node. It's just always going to find the shortest path. And if it doesn't, then that implies that it didn't actually expand that way, that it didn't actually do what it says it's supposed to do. Which is a proof that you'll write in, I think, 250 these days. You'll prove that breadth first search always does find the shortest path in terms of number of edges. Breadth first search is an algorithm. You can manipulate it to return whatever you need it to return. Yeah, I mean, to an extent. If you modify it too much, it's not going to be breadth first search anymore. But in concept, you're right. You can modify anything. You can modify this till it's, YouTube's algorithm eventually. You can't really call it breadth first search at that point. But that is the whole idea of teaching you how to do these things, is that you shouldn't be restricted to like the algorithm that I give you or really anything. You can write code to do whatever the hell you want. You want code that does, makes your wildest dreams come true. Go write that code. Go have a computer do that for you. Train that computer to do it for you. You can modify any code to do whatever you want. Yeah, this doesn't return anything. This intentionally returns unit because I want you to modify this code. I don't want to give you the answers. I don't want to have this return the answer to LT5, for example. I don't want to give that to you. This returns unit, but you should have it return something in your code, in your homework. Do we need an if statement to stop once the DQ end? No. Where's my debugger? So that's what this while loop does. A while loop is going to run until, as long as this condition is true, this while loop is going to keep looping. So once the queue is empty, this while loop is going to say, oh, my condition is false. And execution is going to jump to the end of the while loop. That loop ends. And then in this case, the method ends. And then returns the unit. So you could add a conditional to stop when you reach the end location. I think it's easier just to let the whole algorithm run its course. And then at the end, you're going to have a data structure with, for LT5 at least, a data structure with the distance from the start node to any node in the graph. And then just look up the end node in that data structure. The minuscule amount of performance gain you would get by cutting the algorithm short once you find the end node just isn't really going to affect us in this case. Yeah, as long as you're just adding things, as long as you keep this structure and you're just adding more data structures and squeezing more information out of the algorithm, then it's still breadth first search. But once you start modifying fundamentally what this is, like for example, if you use a stack instead of a queue here, fun fact, you swap this stack with this queue with a stack, and you end up with depth first search. Just with one simple change. So let's keep stepping through this thing. We're exploring the neighbors of 6. The first neighbor is 5, which I believe we've explored. 4, we've definitely explored. And we're done with the neighbors of that. In our queue is 5, 11, and 7. 5, we're going to explore 7. 7's clearly explored because it's in our queue still. 6, I believe we've explored. 2, we've definitely explored. And we didn't get any new information there. Explore the neighbors of 11. Start with 8. I'm quite certain we explored 8. 10, I'm not sure if we explored 10. No, we didn't. So get 10 in our data structures. Done with the neighbors of 11. Explore 7. Node 9. We didn't explore either. 8, we've explored. 5, we've explored. And we're done. Our queue is now 10 and 9. Exploring 10. Its neighbors 11, we've explored. 12, we have not explored. What node is 12? 12 case. All right, so our queue is 9 and 12. 9. Exploring 7. Nothing to explore. And 12. We end up with an empty queue if we don't explore anything here. We have reached the end of this algorithm. 10 has been explored. 9 has been explored. And we're at the end of the algorithm. So now we have an empty queue The while loop is going to end. The method returns, and then this example code just doesn't do anything. And the program ends. Yeah, the idea for the path, instead of storing, I did this all in the slides. Instead of storing the distances, you store the ID of the node from which you came. Instead of the distance of the node that explored that node plus 1, you store that node's ID itself, and then you can backtrack. It was all explained on Wednesday. There shouldn't be any general questions about how to do the pathing. You should have specific questions at this point. And then in a while loop, while the node I'm looking at is not the start node, keep appending or prepending to a linked list that is your path. Any questions on this? Yeah, quiz responses should be pretty long, though. 30 students have finished the learning objective part of the homework. So, best case, that's like half of you who are here right now. LT5 hints. I literally just went through LT5. Like, everything I just said shows you how to do LT5. I don't know what else I can say about LT5 without typing the code for you, to be honest. I've really explained it to death. Kind of gave the answer multiple times, too. I did it once in slides and once in code now. But aside from literally typing up the code for that map for you, I don't know what else I could do. Yeah, I hope you were joking on that, the doctor. So let's take a look at this level as graph method that I give you. And actually have to pull. If you haven't pulled the new code, make sure you pull it. You should have these extra checks on the conditional here. LO5 one. There used to be an LO5 just last semester. LT7 hints. Yeah. So this level is graph. This is where I'm creating a graph. Just like we did in the code that we just saw, except in the code we just saw, I hard-coded, I just manually said, add these nodes and add these edges between these nodes. We want to do the same thing, except we're using these wall locations, level width and level height, to decide exactly how to create this graph. So I'm going to create the graph of grid locations and store grid locations at the nodes. And those grid locations are all going to get IDs, which are determined by this function. So I'm going to take the Y location times the width of the level plus the X location. So what this means is if I have I'm going to Google it again. I think it was helpful when I pulled up images. So if I have some grid, let me find one that doesn't hurt my eyes. So if I have some grid like this, what I'm doing is labeling these 0, node 0, because this is 0, 0, so 0 height times 0 times the width of the level plus x, so 0 plus 0. 1, 2, 3, 4, 5, 6, 7. And then when I get to the next row, I'm going to take the y value, which is now 1, multiply that by the width of the level, which is 8 in this case. So I have 8, and then add the x value, and I end up with 8 for this node. Then 9, 10, 11, 12, 13, 14, 15. Then I end up with 16 here. This is 2 times 8 plus 0. 2 times 8 plus 1, 17. 2 times 8 plus 3. So what I'm doing is numbering the grid locations from left to right, top to bottom, and just giving them numbers as you would read a page, as you would read text on a paper. That's how I'm numbering the cells. So I'm turning these two-dimensional grid locations into a one-dimensional ID by using this equation. This is fairly common. It's a fairly common numbering system. I believe you've seen this in 115. I think that question's still alive in UB Infinite, where we say, how do you turn these two-dimensional things into one-dimensional things? And vice versa. You can go backwards, too. If you have a grid ID, you don't have to do this for the homework. If you have a grid ID, divide it by the width of the level and use integer division. That'll give you the y coordinate. And if you take it mod the width, you'll actually get the x coordinate. So divide it, integer division with the width of the level, that's your y, and modulo the width of the level, that's your x. So you can actually go back and forth if you need to. We don't need to on this homework, but when we number like that, we do get that feature. So that's how we're converting grid locations into IDs in the graph. And since that has a very specific structure, it means we can take advantage of that when we're working with this graph. So when you have a grid location, you can use this same function to look up the grid ID, the node ID in the graph for the grid location at that XY position. Yeah, level as graph is tough. So this used to be required. I used to not give this for similar versions of this question for pathfinding. And this was the bulk of the questions in office hours, was how to generate the graph from the level, which is less about data structures and algorithms. So I always was upset that so many students were spending so much time on this part of it. This was supposed to be an easier part. So to avoid that, I just gave it to you this time. How would you like us to cite stuff copied from your examples repo? If you're using it for homework in 116, you don't have to cite it at all. I'll know it's my code. Like, if it hits my AI radar, I'm just gonna be like, oh yeah, it's my code from the examples repo, whatever. Outside of the course, I don't know. If you want to put a link to it, that's fine. I'm pretty open about students are allowed to use my code that I give them. I created that code specifically to help you learn things. As long as you're learning from it, I don't really care about attribution. Unless you're like copying the whole repo and teaching your own course or some silly crap like that. You know, be reasonable. But if you're using it to help your learning, I don't really care. I don't cite anything. Maybe you should, Priest. And citing in code is pretty easy. Like if you cut and paste this in your code somewhere else, just put it github.com/Hartloff/CSE116-examples. Bam, cited. We don't have to worry about MLA format or anything like that. Just like put a link right there. Maybe get your HTTP. Bam, cited. It's not that hard. If you're not citing your code, start doing so. So we use this function to get the ID for each node. I'm going to iterate over... Oh, I was wondering why you asking that, Priest. Yeah, because I forget I used that code. So this is going to be a nested loop where I'm iterating over I from 0 to the level width. And for each value of I, I'm iterating over j from 0 to the level height minus 1. Until is going to be exclusive of the endpoint. So this is basically a nested for loop. I could split this into 2 for loops and have the j loop inside the I loop. This is some Scala syntax, which makes us lets us do that a little cleaner. And then I'm going to get a grid location at that XY, or IJ in this case. And then as long as that location is not one of the wall locations, which the grid location, I can get away with this. I can do this because I have an equals method in the grid location method that checks the X and Y. Otherwise, I wouldn't be able to do that because it would check equality by reference. This contains would be by reference. Since I have an equals method, this contains is going to call that equals method and see if, according to the equals method, this location exists in the wall locations. Because this is a brand new grid location, this reference will not be contained in the wall locations because I just created it. But since I have an equals method, I'm allowed to do this. So if this is not in the wall location, so if this grid location is not a wall, add it as a node in my graph. So now I have every tile that is not a wall as a node in my graph. Next thing I have to do is add the edges. For this, for each node in my graph, I'm going to look to the right one and down one. Those are the two potential grid locations I can add. And for each of those, I'm going to check, did I go, is that a wall? Or rather, is that not a wall? So if that node exists by ID in my nodes, then I know it's not a wall because I didn't add any walls in there. And did I go off the edge? This is the edit that I had to make. Did we go off the edge of the map? I thought I could get away without doing this, but I realized that, after the fact that I can't. Somebody had issues with that in office hours, and I realized why I can't get away with that. It was a silly mistake that I made. And if that's not a wall and we're not off the edge of the map, add an edge between those two nodes by ID. ID from the nodes, and then the new location that we're looking at, the new potential location, convert that to a grid ID using this function, which we used over here, grid ID. I forgot to mention that. Call our grid ID function and add that new location as a grid ID, or with that ID. And then add the edge by IDs after putting the grid locations through this function. Then return the graph. Hey, look at that timing. We're going to say bye to YouTube. Peace out, YouTube.